SwayamPrabha. Digital India. Educated India.
Good morning everybody. Today we will discuss about Prandtl's mixing length and universal velocity profile. As I have mentioned in the last lecture that for the solution or for having the solution of turbulent flow field, the flow field is decomposed into time mean field and a fluctuating field. Equations are solved for the time mean values and closure models are written for the correlations of fluctuations. That means the fluctuating components are expressed in terms of time mean quantities, time mean velocities. Historically, the first attempt in this direction was made by Professor Prandtl, and Prandtl mixing length model has been one of the cornerstones of solving turbulent flow problems. We will discuss today about Prandtl's mixing length and universal velocity profile in a turbulent flow field. We have already discussed about Reynolds averaged Navier-Stokes equations for turbulent flows. Reynolds averaged Navier-Stokes equations need the value of turbulent viscosity or eddy viscosity to get solved. Now, the turbulent viscosity can be estimated by Prandtl's mixing length model. This model does not use any differential equation, and that is the reason it is called zero equation model. The differential equation based models such as the KL or K epsilon or K omega models are more rigorous models. One can also refer to the mathematical paradigm of large eddy simulation or direct numerical simulation. However, we require to have a look at the Prandtl's mixing length model for understanding the first correct approach for determining turbulent viscosity. Now, in the case of turbulent flow, velocity, pressure and temperature at a fixed point in space do not remain constant with time but perform very irregular fluctuations of high frequency. The velocity of the fluid in turbulent flow can be represented by two components, mean motion and fluctuating component. We have already seen this. The velocity of fluid is given by u equal to u bar plus u prime, v equal to v bar plus v prime. This is the fluctuating component. W equal to w bar plus w prime. Similarly, P equal to P bar plus P prime, and temperature equal to T bar plus T prime. We can see a turbulent pipe flow schematic here, and these are the velocity fluctuation of u velocity, and if we average out we get the average profile, and this u, if we plot versus time, we will be able to see these fluctuations, and for steady mean motion we will get the mean motion. However, the fluctuating components do not bring about the bulk displacement of a fluid element. The instantaneous displacement is u prime dt, and if that is indeed not responsible for the bulk motion, we can conclude that between interval of minus t and plus t, u prime dt equal to 0, where t tends to infinity. Due to the interaction of fluctuating components, macroscopic momentum transport takes place. Therefore, interaction effect between two fluctuating components over a long period is non-zero, and this yield, if we perform this integral in time domain, u prime v prime dt, this is non-zero. So u prime dt integral is 0, but u prime v prime dt is non-zero. We take time average of these two integrals and write u prime bar equal to 1 by 2t, then this integral, this is equal to 0 when u prime is being integrated. But u prime v prime bar equal to 1 by 2t, again the integral u prime v prime dt, and when we integrate u prime v prime dt, this is non-zero. So u prime v prime over bar is non-zero. Similarly, we can write v prime bar, w prime bar, and p prime bar, t prime bar, these are 0. Let us explain the non-zero quadratic terms once again. Consider continuity equation in two dimension. Del u del x plus del v del y equal to 0. If we substitute u equal to u bar plus u prime, v equal to v bar plus v prime, and then perform time averaging, we shall obtain del x of u bar plus u prime over bar plus del y of v bar plus v prime over bar equal to 0. If we apply over bar operation, then we can write del x of u bar plus del y of v bar plus del x of u prime bar plus del y of v prime bar equal to 0. Now we know u prime bar equal to v prime bar equal to del x of u prime bar equal to del y of v prime bar. All these quantities are individually 0. So we can invoke del u prime del x bar or del u prime bar del x is 0, del v prime bar del y is 0. From there we will get del x of u bar plus del y of v bar equal to 0. Now if del x of u bar and del y of v bar equal to 0 in this equation, this is 0, this is 0, so we can write del u del x bar, we can write here this is 0 and this is 0. We can write del x u prime plus del y of v prime. So del x of u prime plus del y of v prime equal to 0. So del u prime del x plus del v prime del y is 0, and we can write del u prime del x equal to minus del v prime del y. If we consider momentum exchange between two adjacent layers, then on the basis of the above equation, it is postulated that if at any instant there is an increase in u prime in the x direction, it will be followed by an increase in v prime in the negative y direction. In other words, u prime v prime over bar is non-zero and negative. This is discerned in the next figure, which shows a cloud of data points, sometimes called scatter plot. The dots represent the instantaneous values of u v pair at different times. So for some u, we get some value of v. So if we plot that dot at one instant, at another instant, whatever is the u value for that corresponding v value. So if we keep on plotting that, this is called scatter plot. So at a given point we can do, at different points we can do that. At every instant we can measure u and corresponding v, and then we plot this. So the plot will look like this. For unit area, so let us consider a plate and the formation of boundary layer on the plate. Flow over a flat plate, and this is turbulent flow over a flat plate. For unit area of the plane PP, the instantaneous turbulent mass transport rate across the line is, because of fluctuation, if there is any mass transport across this PP line, this has to be then rho into v prime. Associated with this mass transport is a change in the x component of velocity u prime. So whenever there will be any fluctuating component in the y direction, which is v prime, it will be accompanied by a fluctuation in x component, that means u, and if v prime is in the positive direction, then u prime will be in the negative direction. Why? The net momentum flux per unit area in x direction represents the turbulent shear stress at the plane PP, which is rho u prime into v prime. When a turbulent lump movement is in the upward direction, that is u prime, and that is v prime, sorry, when a turbulent lump movement is in the upward direction, that means v prime is the fluctuation, and if it is in the upward direction, we can write v prime greater than 0. It enters but immediate at the next level or next layer, it enters a region of higher u bar, because this is variation of u bar, the mean velocity profile. So it enters a region of higher u bar and therefore likely to affect a slowing down fluctuation in u prime. So whatever is the value of u bar here, at the slightly upper level, that velocity of u bar is more. So when this v fluctuation is reaching there, it will have a tendency to share the momentum with the next layer, and the upper layer, which has a greater mean velocity, will be slowed down. So slowing down this will affect a slowing down fluctuation in u prime, that is u prime is negative. A similar argument can be made when v prime is negative. When v prime is negative, that means v prime is coming to the immediate lower layer, and immediate lower layer, the u bar, the average u velocity, is less than this layer. So this momentum will try to accelerate the lower layer. So in the lower layer, then v prime will be positive. Sorry, u prime will be positive because of negative v prime. So let me repeat again. When v prime is in the upward direction, it will reach immediate next layer where u bar is having higher velocity than this dotted line location. So v fluctuation is going from a level where u bar is less than the upper layer. So effect on the upper layer will be basically u prime in the negative direction. When v prime is coming in the lower direction, that means v prime is negative, and at the immediate lower layer, u bar is having less value than the level of this dotted line. So v prime with higher u bar will reach the layer where u bar is less, and this will have an accelerating effect on u bar, creating u prime greater than 0. So for positive v prime, u prime is less than 0. For negative v prime, u prime is greater than 0. And this turbulent shear stress will be given by minus rho u prime v prime over bar. Again, let us imagine a turbulent fluid lump which is located a distance L above or below the plane PP. These lumps of fluid move back and forth across the plane and give rise to the eddy or turbulent shear stress effect. At y plus L, this L is very small, the velocity would be u bar y plus L. If we expand in Taylor series, this will be u bar y plus L del y of u bar. While at y minus L, we can write u bar y minus L equal to u bar y minus L del U bar del Y. And again, let us recall that L is very small, so that we can expand in these expressions in Taylor series. Prandtl postulated that the turbulent fluctuation is proportional to the mean of the above two quantities. So, if we try to get turbulent fluctuation from these two expressions, according to Prandtl, U prime is proportional to L into del U bar del Y, or this proportionality is converted into constant equality. We introduce a constant U prime equal to C1 arbitrary constant L del U bar del Y. Here L is the Prandtl's mixing length. This is analogous to mean free path, that is the average distance a particle travels between two collisions according to kinetic theory. Now, this molecular transport problems, the way we define the average distance a particle travels between two collisions, that is mean free path, and Prandtl's mixing length in case of turbulence mixing, it is analogous to mean free path for molecular transport problems. Prandtl also postulated that V prime is of the same order of magnitude as U prime, so that V prime can also be written another constant C2 L del U bar del Y. Now, the turbulent shear stress is given by minus rho U prime V prime over bar. So, we can write rho L square del U bar del Y whole square from the expression of U prime that we got, and from the expression of V prime we can summarize in this way. And we can clearly see C1 and C2 can be included in unknown mixing length. And then if we want to express this in terms of turbulent viscosity, we can write rho nu T, turbulent kinematic viscosity, into del U bar del Y. So the eddy viscosity, turbulent viscosity, we can express as then from this expression L square into modulus of d del U bar del Y. L square modulus of del U bar del Y. This is nu T, or turbulent viscosity or eddy viscosity, and we are just giving identification to it. Now consider the boundary layer on a flat plate. The shear stress due to laminar flow is given by mu d U bar dy. Now the total shear stress is then laminar shear stress plus turbulent shear stress. So rho nu, this is basically fluid property, del U bar del Y, plus rho nu T, this is not fluid property, this arises out of mixing, del U bar del Y. Combining them together, we can write rho nu plus nu t del u bar del y, and we are giving a identification B. Now the turbulent viscosity nu t in equation A, this turbulent viscosity in equation B can be determined from equation A. Okay, so because here nu t is unknown, but nu t can be written as L square modulus of del u bar del y. However, so nu t, even if it is substituted by L square del u bar del y, we can do that, but our problem is still not solved. How to determine the value of L? Because nu t is unknown in this equation, and nu t from the previous equation we get L square del u bar del y. So nu t apparently is obtainable, but we have to know the value of L. So how to determine the value of L? The mixing length. Several correlations using experimental results of tau t have been proposed to determine L. In the regime of isotropic turbulence, the most widely used value of mixing length is given by L equal to chi y, where y is the distance from the wall and chi is known as von Karman constant. So this Prandtl mixing length, it was a big challenge to know what is the value. Prandtl said it must be very small, but what is the value of this mixing length? And several experiments were done, and from that it was concluded that L equal to chi into y, that means distance from the wall, and chi is a constant. It's known as von Karman constant, and its value is very close to 0.4. It varies between flows, from flow to flow it varies, but the value is close to 0.4, 0.38, 0.39, 0.4. These are the values were obtained through several carefully done experiments, and finally it was concluded that chi can be taken as 0.4. Now this is basically again the different zones over a flat plate for turbulent flow have been just schematically drawn. Very close to the solid wall, it is viscous sublayer. Next to it is called buffer zone, and then far away it is fully developed turbulent velocity profile, and it's given by some mathematical expression which we will see will be well represented by log law. And here this viscous sublayer has been little bit magnified. Viscous sublayer in actual dimension, it is much smaller than what has been schematically presented here. Now, universal velocity profile on a flat plate. Usually, if the flow is turbulent and it is fully developed turbulent flow with high frequency fluctuations, the velocity profile has a log law based shape, and this does not vary really from flow to flow so long it is dominated by high frequency fluctuations, and this profile is called universal velocity profile. A very thin layer next to the wall behaves like a near wall region of laminar flow. That's what is this region I'm calling, which is viscous sublayer region. The layer is known as laminar sublayer, and its velocities are such that the viscous forces dominate over the inertia force. Again, this figure. No turbulence exists in the sublayer. As it has been stated that in the near wall region, inertia effects are insignificant, and we can write then nu del 2 u bar del y2 minus del y of u prime v prime over bar. So inertia terms are not there on the left hand side. Flow over a flat plate, pressure gradient is 0, and the viscous term together with turbulent shear stress term are the stress component on the right hand side. So we can write nu del 2 u bar del y2 minus del u prime v prime over bar del y equal to 0, which can be straightforward integrated as nu del u bar del y minus u prime v prime equal to constant. Just integrate with respect to y. Again, we know that the fluctuating components vanish near the wall. So, fluctuating components very close to the wall in the sublayer region, they do not exist. So, the shear stress that is created on the wall is basically created by the average velocity. So, nu del y of u bar equal to the shear stress by rho. Actually, it is mu del u bar del y is tau w. Since we are taking nu here, so we are dividing tau w by rho. And this can be written as u bar minus 0 from wall to just the next y within the sublayer, very small distance in the normal direction. So there the velocity, if we say u bar minus 0 at the wall and distance is y minus 0 is given by tau w divided by nu rho into nu. Actually, we are just writing this equation nu del u bar del y. We are transferring nu on the right hand side, and between a very small distance from the wall, we are writing this as u bar minus 0 divided by y minus 0 from the wall, tau w divided by rho into nu. And tau w by rho can be substituted by u tau square. So tau w by rho we are substituting by u tau square, and we are writing this as u tau square by nu, where u tau is given by root over tau w by nu, and this u tau is known as friction velocity, given by tau w by rho root over u tau. This is friction velocity. So from the aforesaid expression, then we can rearrange and write y u tau by nu equal to u bar by u tau. And this gives us a non-dimensional coordinate which is called y plus. Non-dimensional coordinate, it is defined as y plus is equal to y u tau by nu. It's a non-dimensional distance given by y plus. And we write down the variation of the non-dimensional velocity. So this non-dimensional velocity we write as u plus. So u bar plus equal to y plus, and within the very thin laminar sublayer, this is linear relationship. U bar plus equal to y bar. But this is in u bar plus equal to y plus, and this is in y plus scale. Y plus scale is very, very small. If we try to estimate, we will be able to appreciate that. Now, that's what I said. So velocity variation in the sublayer is linear, where u bar plus equal to y plus, and this is y plus scale. And I have already mentioned this is very small, but here we have magnified it a little to understand this linear profile. In the turbulent zone, the turbulent shear stress from Prandtl mixing length model, that can be, we have already seen, turbulent shear stress, because that's what we have told, that basically if this is L and shear stress is basically given by nu t, and nu t is given by L square del u del y. So now we can write tau t is equal to rho L square du dy into del u del y. So basically nu is L square du dy multiplied by del u bar del y. So we can write tau t equal to rho L square del u bar del y square. So where L is the mixing length given by chi into y, and chi is a Kalman constant, and we can write, if chi L equal to chi y, chi is von Kalman constant, we can write tau t by rho L square will be chi square y square, and this y is the distance from the wall, del u bar del y squared. So tau t, turbulent shear stress in the turbulent region. We are now not in the viscous sublayer region. We are considering the dynamics in the fully developed turbulent flow. So there tau t, turbulent shear stress by rho, is chi square into y square into del u bar del y squared. Now here just recall that we said this is very thin, just little magnified, very thin. So you take this profile which is linked to shear stress, turbulent shear stress. This profile goes very close to the wall, and between when this variation becomes linear, that region is the viscous sublayer. So basically, whatever is the shear stress at the edge of viscous sublayer, that shear stress is turbulent stress, and that is transmitted to the wall. So here if we want to find out shear stress, it will be basically nu us minus 0 divided by del s minus 0. So that will give us basically mu or rho into nu, whatever we write, us by ds. That's what I was saying. Rho into nu or mu multiplied by velocity gradient will be given by us minus 0 divided by del s minus 0, which is finally mu into us into del s. So shear stress in the turbulent region dictates the velocity us at the edge of the sublayer. The wall shear stress is equal to turbulent shear stress at that point, and we get the quantity now. This quantity is mu us, velocity at the edge of sublayer, divided by del s, thickness of the sublayer. So if that is known, then we can substitute that here. And this is TW. Now again, if this is TW, we know TW by rho is friction velocity square, u tau square. So we can write this as u tau square and transfer chi and y to this side. So we can write, instead of this, we can retain del u bar del y square on one side, and on the other side u tau by chi y whole square. So del u bar del y square equal to u tau by chi y square. And we can write this because the wall shear stress is equal to turbulent shear stress. So fully developed turbulent profile at the edge of laminar sublayer or viscous sublayer, the turbulent shear stress, whatever is created, that is equal to wall shear stress. And then equating that shear stress with wall shear stress, we substitute wall shear stress by rho as u tau, and we can write this equation. And if we integrate this, we will get u bar equal to u tau by u bar equal to u tau by chi into ln y plus constant. Integration. We can rearrange that u bar by u tau equal to 1 by chi and ln y and constant. This we can write ln y minus ln y0. Where this can be viewed as a constant. Now y0 is very small, and the small quantity we can define as beta, which is very small, into nu by u tau. Then if we substitute y as beta by nu, beta into nu by u tau, finally calculation of this term, since u tau is small, nu is small, and beta is very small, is a very small quantity. And from here we can rearrange, we can transfer u tau and nu with ln y, and we can write u bar by u tau equal to 1 by chi ln y u tau by nu minus ln beta. And as I said earlier, this is a small quantity and constant, so we can write u bar plus equal to a1 1 by chi it gives a constant A1 ln y plus, this is in y plus scale, u tau by nu is y u tau by nu is y plus, so ln y plus this 1 by chi and ln beta together gives another constant plus d1. So this is the log law velocity profile or fully turbulent flow velocity profile, and this is universal in nature. These constants were determined from experiments. For smooth ducts or smooth plates, A1 has been observed as A1 equal to 2.5 and D1 equal to 5.5. So we can write U bar plus equal to 2.5 ln y bar plus 5.5. Also, if we write it in a slightly different way, we can write U bar plus equal to 2.5 ln E y plus. We can, instead of writing separately the constant, we can write the entire quantity in this bracket with ln, and then E will be 9.0 for smooth walls. Finally, log law is defined for the turbulent zone as U bar plus equal to 1 by chi ln E uppercase E y plus. The constant chi is known as the von Karman constant. The location where log law profile and linear profile meet can be calculated. So it is really of interest to find out this location, this distance from y plus, where basically this log law profile, which is the profile for fully turbulent zone, and this linear profile, which is the profile for the viscous sublayer, they merge or they meet. What we can do, the location where log law and linear profile meet, this is the log law profile, U bar plus equal to 1 by chi ln E y plus. And the equation for linear profile is U bar plus equal to y bar plus. So if this U bar plus is substituted by y plus and we solve, so log law profile is given by U bar plus equal to 1 by chi ln E y plus, and the linear profile is given by U bar plus equal to y plus. So in this U bar plus, if we substitute y plus and solve for y plus, we'll get the location of y plus where linear profile and the log law profile meet. It is given by 11.63. So 11.63 y plus unit. In order to estimate how small it is, we can say that y plus, in terms of y plus, the boundary layer thickness is around 1500 units. So we can imagine how small is y plus. If we want to compute, the grids near the wall has to be very, very fine to take care of this y plus equal to 11.63 or 12, roughly that distance. Thank you very much. Thank you for your interest.